All right, so we talked about geometric sequences, and we talked a bit about arithmetic series. But again, a geometric sequence is just a list of numbers that follow a geometric pattern, right? Where there's a common ratio, there's a multiplication between each term and the next. Right? But I'm just listing them in a sequence, right? These commas are telling me it's a list. The geometric series is a sum of all terms. So I write addition between, or subtraction if the term is negative, right? This is the same thing as 2 plus, -4 plus, +8 plus, -16, right? And so on and so forth. And I can add up these terms with a few different formulas. Now, because we don't know a lot about exponential functions here, we're going to just kind of tell you the formulas here. So here are the formulas. So if I have an infinite series, so I don't know last term, right? I don't know the nth term, Tn. Then here's the best formula for me to use. It is Sn is found by taking the first term, multiplying it by r to the n minus 1. Notice that minus 1 is now not in the exponent, over r minus 1. Specifically in the case where r cannot be 1, which isn't really a sequence anyway, because if r is 1, nothing is changing from one term to the next. If I multiply by 1, nothing changes. If I do know t of n, right, if I know some last term, I can simplify things a little bit, and I can say the sum is found by taking r times the last term, subtracting the first term, and dividing by r minus 1. So again, looking at the variables we need, here I need a t1, here I need a t1, so they both need t1, or you could be solving for t1 if I tell you the sum. They both need r, right? I need to know that common ratio. Oh, let's choose a different color. So I need to know my common ratio for both of these formulas. Notice this one needs me to know n, but it doesn't care about the value of n, right? I just need to know when to stop adding terms. Right, whereas this one needs t of n. Right, so if I know the last term, then that's fine. I don't need to know what position it's in, which is even better than our series formulas for arithmetic series. Right, so if I have if I have 3 of these 4 things, because they both also talk about Sn, if I know these 3, I can find the sum. Or if I happen to know maybe like these 3, I can find t1, depending on the information I'm given. Right, so it's mainly a difference of between, do you know the value of the last term, or do you know the place that it's in? And again, just like arithmetic series, when I talk about finding the sum, I'm talking about finding the sum of the first n terms. So if I want to find the sum of the first 7 terms, I'm talking about S7. This is an infinite series. I know n, which is great, right? I know n, that's what I wanted for that first version. I don't know the 7th term, so I'm going to use this formula. I know Sn is t1 r to the n minus 1 over r minus 1. So taking some inventory of what I know, what I have, my first term is 4. I'm talking about 7 terms. My common ratio, right, so what gets me from 4 to 12 and then 12 to 36 is multiplying by 3. So my common ratio is 3. And I'm trying to find the sum of those 7 terms. So I just plug everything in where it goes. First term is 4, 3 to the 7 minus 1. Again, notice that 1 is not up in the power like it used to be. And so I can plug this all into my calculator, or I can kind of solve it bit by bit, piece by piece. Oops, little typo here. Sorry, that should have been a 3 on the bottom. So I'm doing 3 to the power of 7 minus 1. So 3 to the power of 7 is 2,187. So minus 1 is 2,186. I'm doing 3 minus 1 on the bottom. So I take that 4 times 2186, which is 8744, divided by 2. And the sum is 4,372, which seems really big, but again, you think of how these terms are growing. My fourth term is suddenly 36 times 3, so 108. And then 3 times bigger than that is 324. 3 times bigger than that is almost 1,000, right? So these numbers grow pretty quickly with those R values. So same thing here. I have an infinite series. I'm going to try out the same formula again. R minus 1. My first term is 1/27. I'm talking about 9 terms. So I'm looking for the value of those 9 terms summed together, right? Added up. Now, when I find my R, it can be a little tricky to recognize. It is times 3, but if you're ever not sure, right, take some number 1/9 divided by 1/27, right? Use your fraction rules. That's 1/9 times 27 over 1, right? I kiss and flip. I have 1/9 divided by 1 over 27. So 1/9 times 27 over 1 reduces down to 3. So my R value here is 3. So I take my first term, 3 to the power of 9 minus 1 over 3 minus 1, which is 2. 3 to the power of 9, 19,683 minus 1, 19,682 divided by 2. If I take that number and divide it by 27, right, it doesn't give me a great number. It gives me a fraction. It actually doesn't even reduce at all. And then I divide that number further by 2. It gives me 9,841 over 27. And that's as simple as I can write it. And that's okay. But at least I've turned it back into a fraction. Again, mostly just using my calculator. I'm not super stressed about you simplifying these fractions by hand, especially ones with denominators like 27. So let's look at a finite series now. Let's look at something where I know the last term, and then I won't need to know what term number this is. All right, I have no idea what term number this is, but I know its value. I know its value is 10,240. So let's use that finite series formula. So it's R times T of n minus T1. Notice there's no brackets here. The R is just multiplied by the last term, R minus 1. Where my first term is 10, my R, notice the change in signs. Notice it changes to subtraction. That's an indication that my R is a negative value, so R is -2. I don't care about n, but I know the last term, Tn. And so I'm finding the sum of the whole series. So I'm going to continue to just write Sn because I don't know how many terms I'm adding up, which feels like a weird thing. But if it works, it works. So -2 times that last term minus that first term divided by -2 minus 1, keeping an eye on your signs here. 10,240 times -2, -20,480 minus 10 over -3. gives me 6,830. Notice that it's positive, right? Because this last term was positive. If I had gone up or down by 1, I probably would have gotten a negative sum, because the term right here would have a negative value. The term right here would have a negative value that's even bigger than 10,000, right? So keep in mind, when I'm adding together, when I'm finding sums of things with negative R values, it could be positive or negative depending on where I choose to end. Let's do another infinite series. Find the sum of the 10th term. Again, I don't know the 10th term, so I'm going to go back to this one. Where my first term is 4, my R value is -2, N is 10, and I want to find the 10th term. So I fill in all the blanks. And here's where I need to be careful. And it's right here. And it's because I need to make sure if I'm plugging this into my calculator, I'm putting that -2 inside brackets. Because if I take the -2 to the power of 10 without brackets, it's going to spit out a negative sign when it should spit out a positive sign. Right? And so -2 to the power of 10, if done properly in your calculator, is 10,024, not negative. Sorry, 1,024. So be careful of that negative sign. Watch your signs. Put brackets around your whole base, which if it's a -2, you can use the negative sign. Just make sure it's inside the brackets. So I'm actually doing 10,023 times 4, and I'm dividing that by -3, and it does give me a negative answer, right? Because every even term is negative. So if I'm finding the sum of an even number of terms, I expect the 10th term should be negative. So -1,364 is the sum of those 10 terms. All right, we'll try one application problem here. The school cafeteria is giving 7 gift certificates away as a prize for perfect attendance. The first award is $2. The next prize is double the previous prize, right? So that's my indication that this is geometric, because double implies multiplication, not addition. So let's look at a little bit of this series first, just to make sure we kind of know what's happening. The first award is $2. It is a series because they're giving away $2 and the next amount and the next amount. So on day 2, or the next day, they give away 4. The next prize, they give away 8, right? And I could write out this whole series, right? 7 terms is nothing crazy. If I really wanted, we could do that, and we could check our answer with it. So 16, 32, that's my 5th term, 64, 128. Some lucky person is getting $128 to the school cafeteria. So the cafeteria wants to know how much money are they giving away? What's the total value of all 7 of these prizes? So what is the sum of all of these terms? Right? Well, math tells me, right, which is not good for this unit, right? I don't want to see this on your assessments, but we can think this, right? 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128. It gives me $254, right? That's not an efficient strategy at all. It does not show your understanding super well of what we're really doing here, the communication of this unit. But worst case scenario, I have a final dollar amount. I can check my answers with that. Because I went to the process of writing out every term, I could do this as an infinite series or a finite series. And let's do all 3 just to kind of check our work with each other. So if I'm using my infinite series, the sum of these 7 terms is found by taking the first term, T1, multiplying by R, which double means it's an R value of 2. right, times 2 each time. There's 7 terms, minus 1, over 2 minus 1, which is just going to be 1. 2 to the power of 7 is 128. I multiply by 127, which is 254. Would you look at that? From a finite series perspective, I can take r times my last term, which was 128, minus my first term, which was 2, divided by r minus 1. So I can take 2 times 128, which is 256, minus 2, and same thing. It gets me to 254. So again, it just depends on what information you're given, what information you know, but all of these are telling me total prizes awarded total to $254. So I'll leave the last one for you to give a try, and we'll look tomorrow at infinite geometric sequences.